right, so this session is on AI for robotics and automation. We've got a full session, surprisingly, and so our first speaker is from Georgia Tech. This is Nadoon. He'll be talking about automating agriculture and food processing with robot learning. So for all the speakers, I'm going to, at 10 minutes, I'll hold up my, or at 12 minutes, I'll hold up my card. There's 2 minutes remaining, and then hopefully leave a minute for questions in there. But we do need to keep on schedule. So.
All right, thank you, Bobby. Good morning, everyone. My name is Nadoon Ranawaka-Arachige. I am a PhD student at Georgia Tech, and today I'll be talking about robot learning and why it's a promising method for automation in agriculture. So, when we talk about automation and robotics in agriculture, we typically assume that we have access to some sort of privileged information or a modeled environment, right? Things like robot dynamics or object poses. But unfortunately, having access to that is quite difficult in agriculture. When we think about the variation in objects in agriculture, if you take one class of objects, say apples, there's a ton of variation in terms of shape, size, color, and other features. Furthermore, we work in very difficult and challenging environments, which might be muddy, wet, flooded, overgrown with foliage. And finally, there's a ton of diversity in the tasks that we want to do as well, right? So trying to program robotic routines for each one of those can quickly become infeasible and intractable. What we need is a paradigm that allows us to quickly scale up robotics in agriculture. So this is where robot learning comes in, with the goal being to have robots autonomously learn how to perform different tasks, right? And with this, the robot learns a model of the environment itself, so it learns all the physics, all the dynamics that it needs to go ahead and perform the task by mapping raw sensor data. So imagine you have cameras, you map raw pixels to actions through a control policy that is learned autonomously. So there are different ways to do this. One of it is reinforcement learning, just quite difficult to do in the real world because it's expensive, right? Another way, which is more feasible, is through expert demonstrations, which is what we call imitation learning. And so today I'll be talking mostly about imitation learning. So before we go into the details of how that's actually done, this is what a typical hardware setup would look like for doing imitation learning. Here we have a robot cell with 2 rigid manipulators, UR5s. We have cameras all the way around to help capture that data during the demonstration, and then you need a teleoperation device, which a user will use to actually demonstrate a task. And you have some compute. A typical consumer workstation with a single GPU is sufficient to train your model and then actually deploy it as well. So at Georgia Tech, we do a fair amount of research in poultry processing. Poultry is a huge industry in Georgia, over $4 billion in farm gate value and over $28 billion in total economic impact to the state of Georgia, right? So in poultry processing, there is a specific step where we have to portion out chicken breast into, say, chicken tenders or chicken nuggets, which is mostly automated. It's done through a water jet machine, but at the beginning of this process, it has to be loaded onto a conveyor. The chicken breast has to be loaded onto the conveyor, and this is done manually, right? So people stand on either side of the conveyor and pick the chicken breast out of the bucket and then put it on the conveyor in a specific orientation because it needs to feed into that water jet machine. So we wanted to see if we could go ahead and automate this process. So the first step here is to collect demonstrations of that task. Here we have a simulated setup where we're picking up that chicken breast and aligning it on the tray on the right to simulate how it would feed into that water jet. As you can see here, this is quite easy to do for even someone without any robotics experience or any programming experience, right? They're just using a VR joystick to teleoperate that robot. At the same time, we have all these cameras around the work cell which are saving all that data, all that camera data, and trying to match it up to what the teleoperator is doing. So we collect that data 50 to 100 times. So we collect a bunch of demonstrations with the chicken breast in different orientations. Here it's again rubber chicken breast. In different orientations, we save all that data into a data set which is minimally processed. So this is something I really want to emphasize. This data set doesn't have any privileged information like object bounding boxes or object poses. It's minimally processed raw sensor data. And then we train an end-to-end model from trying to map the raw pixels to the robot actions that the teleoperator demonstrated by using a large neural network, right? Very briefly, we have a vision encoder that extracts the vision features, and then for generating actions, those vision features get passed into a diffusion model that actually generates those actions. These actions, again, depend on your specific robot, but here we're using 7-dimensional actions. So we have the XYZ position and the roll, pitch, yaw rotation of that end effector of the robot, right? So that's what the model is predicting, where the robot needs to be and whether the gripper needs to open or close. And so once we have that model trained, we can actually roll it out on the real robot, right? So what we do is we take the model, we give it that sensor data, the raw pixel data, and then it predicts what the action needs to be. And once those actions are predicted, those are sent to the robot controller at 20 hertz, which means 20 times a second. The model is predicting where the robot's end effector needs to be and what it needs to do, right? So now the model is doing this completely autonomously without any additional input from the user. Here we're doing it with real chicken breast. So what we did was we collected a ton of most of our demonstrations with the rubber chicken breast, and we collected a few fine-tuning demonstrations with real chicken breast. We can see this gives us very powerful performance, and the model actually ends up working real well. So for us to get to this stage, it took us about 4 months to build up all the infrastructure, to try out different network architectures and actually train the model, right? So you might think, okay, well, what's the point? You could come up with a classical method that probably does this just as well in that amount of time. And here's the benefit. We wanted to look at another task. This task is called co-loading in poultry processing, where you pick up a chicken and put it on a cone for the processing. So 4 months to do the pick and place task, and then we use that same recipe, that same pipeline, with 2 additional hours of data, right? 2 hours of data collection, we were able to train a whole new task. And if you look at it closely, it even has a different gripper, right? It's a suction gripper. Previously, we had a 2-finger gripper, but the formula is exactly the same, right? So this allows us to very quickly scale up the different tasks that we want to do. Additionally, with robot learning of these models, we get what's called the robust closed-loop behavior, right? One example of this is here on the left, where the model picks up the chicken breast, drops it, recognizes it, drops it, and goes back to correct its error and pick it up again, right? If you were to try and program, using classical robotics, then you have to have routines in there for that error recovery behavior. We have a state machine. We didn't need to do any of that. We didn't write a single line of code that taught the robot how to do this, right? Additionally, it can react in real time to changes in the environment. Here we're teaching it how to do like a packing task with peaches, pack those peaches into a box. And while it's packing the second peach, I go down and put down another peach on the tray, and it reacts to that and goes and picks up that peach, because it knows that whenever there's a peach on the tray, it needs to pick it up and put it in the box, right? And again, we never explicitly program this behavior in. It's sort of an emergent behavior through the neural network. So, with that being said, robot learning is definitely not a complete topic, right? There are tons of areas of improvement and challenges that still need to be addressed, like how can you improve the performance of these models, how can you make them safer, more efficient, more explainable, how can you use sim-to-real transfer. Won't have time to talk about all of those, but I will talk about a couple of those today. So, when it comes to improving the performance, what this was a work that came out of Stanford, led by Ajay Mundakar. And what the key insight for this is that the robot is likely to fail, right? The model is likely to fail in these what we call bottleneck regions. So there are certain parts of the task that are more difficult to do, right? That may involve more complex motions or more precise maneuvering, right? So the insight here is to have a human supervise over the robot, and when they feel like it's going to fail, they're going to go ahead and intervene, prevent the robot from failing, and give it additional data on how to perform, on how to navigate that bottleneck region. In practice, this is what it looks like. We let the robot do most of the task once we have a baseline model trained. We take over control when we feel like it's going to fail, right? Help navigate that, and then hand over control back to the robot. So by providing that additional input for those bottleneck regions, the model is able to focus more on those regions and learn how to improve its performance. So with this, we're able to double our performance for the co-loading task, and it's, in general, for most of our tasks that we tried out, we're able to improve the performance. Another critical challenge is safety. Since this is an end-to-end model, right, a complete black box model that maps pixels to actions, we don't really know what's going on inside the neural network, right? And so this doesn't really work for a lot of us, for a lot of stakeholders and sponsors, right? So at Georgia Tech, we have this project led by Won-Suk Jung, one of my colleagues, which tries to wrap a safety filter, a more classical safety filter around the imitation learning model, right? So whatever the imitation learning model or the AI gives us as actions, we try to simulate out what would happen if those actions were executed very coarsely, right? So again, not much privileged information. We can set up exclusion zones around the robot that we say we don't want the robot to go into these regions or hit the workspace. And then we look at what would happen if the actions executed by the imitation learning model were actually sent to the robot controller, right? And if those were to violate safety constraints, what we can then go ahead and do is take over control and prevent the robot from actually executing those actions, bring it back into a safe state, and have the model replan from then on. So when it comes to opportunities for those of us who work in agriculture, robot learning is a very powerful paradigm because it allows us to upskill workers. No longer do you need a 4-year or PhD degree to actually become a robot operator, right? It's very simple. You just use a VR joystick or some other sort of computer interface to go ahead, provide demonstrations, and train robots. At Georgia Tech, we're developing these VR environments for actually providing demonstrations on supervising robots as well. So the idea is we improve the working condition here and have people pretty much anywhere in the world that could remote into work. So no longer are they working in those demanding, dangerous environments, right? But they're still not being replaced either, right? So people are still having jobs, but we enable them to work in safer environments. And it also has this added human oversight factor, right? So when the robot's working autonomously, you have a human supervised, and therefore we maintain that trust and safety in the system. Another thing is the variability and scale that we work in agriculture is actually a good thing. When we look at the recent successes with deep learning models, especially large language models, a lot of that has come due to the larger data sets, right? With larger data sets, you get more capable models. So with agriculture, since we're working at such high scales and throughputs, we expect to see a similar trend, right? So with the more data we collect, the more tasks we do, we hope to be able to build more general systems and more capable systems that are robust as well. So really quickly to wrap up, if you think of a long-term vision, you could have the robot teleoperators to demonstrate how to do tasks, we collect data, we train models, deploy those, and then at the same time, we have those people supervise over those robots themselves. That way, we're still maintaining jobs and improving worker efficiency, productivity, as well as maintaining safety. So, yeah, that brings me to the end of my presentation. If you have any questions, definitely feel free to reach out. We'd love to chat to you all about robot learning. And I would also like to thank all my supervisors and colleagues and collaborators at Georgia Tech, as well as the Agricultural Technology Research Program at Georgia Tech for funding this research.
All right. Thank you.
Here are some other tasks if you all are interested. These are all trained with the same pipeline, a few hours of data, no programming at all.
And we do have time for some questions. So, have any questions from the audience? Yeah.
When you have operator control, is that in the learning mode where you're taking over those critical components, or is that in the operational mode, and then does that become a learned function inside of that?
Yes, so it's actually almost like a hybrid. So we have the robot controlling the, we have the model, the AI controlling the robot, and while it's doing that, we have the operator press a button when they want to take over control, and when they do take over control, the model no longer controls the robot, but we start saving the data that the operator gives, right? And so it's not actively learning at that moment, but we save all that data, and then we go ahead and retrain the model afterwards, which doesn't take long at all.
So what's the effect of lighting? You have lighting set up. What's the effect of different lighting? Does it affect the model?
Different lighting. That's a great question. So with the end-to-end models, it can be a little brittle to different lighting conditions or distracted. So the way we get over that is we collect data in all different conditions, right? Or we try to find a way to maintain like a consistent lighting or consistent environment. With some of our newer models, they are actually a little bit more robust if we, especially if we pre-train our vision encoders on a ton of data, we find that they're more robust to different lighting conditions.
All right, I have one question.
Yes.
So you're training the robot, say there's some chicken breast that it, for some reason, can't pick up, just the characteristics of it. What happens then? Does the robot get stuck in a loop trying to pick it up, or is there some kind of, extra wrapper built around that to exit?
Right. So,
Or maybe you never encountered that problem, right?
no, we definitely encountered the problem. So the typical way we evaluate these models is we give a set time limit for the model to complete a task, right? We say, okay, 20 seconds, 30 seconds. If you don't complete the task, then we're going to go ahead and reset the scene. What we can do is we can have some sort of additional sensing on there that detects if the task was actually completed, if it was picked up and placed in the right location. And if it doesn't happen, we could have perhaps a human operator come in
Right.
and demonstrate how to pick up that specific chicken breast. And using that, we collect that data and retrain the model so that never happens in the future.
All right, that's interesting. Really good work. All right, thanks a lot. Our next speaker is University of Auburn. Ahmed, you want to go ahead and pull yours up there? And we're looking at AI-driven robotic inventory of nursery crops. Right. Well, unfortunately, Hamid's not going to be able to finish. We're getting him taken care of. But with that, we've got our next speaker. So that's Anna, right?
Yeah.
That's kind of a bit disruptive to try and follow, but look forward to hearing from you. And our next few speakers are talking about some spray out. So yeah. So with that, let's get started.
So, hello everybody, my name is Anna Buzanini, and today I'm going to present to you about the weed control in the fallow period using a smart spray technology. So, I'll try to give you guys more my weed science vision, and I'll also show you guys that you have the smart sprayer and you're applying the real time, but also how it's important you have a weed management that is combined with this technology. So, Florida is responsible for most of the vegetables and strawberries produced in the United States. So, like just for tomatoes, you're responsible for 52% of the tomatoes that is the production in the United States. And we kind of can do like this production in the whole year, but you have the summertime that's really long and hot and humid. So it's really appropriate for pests and diseases. So most of the birds are gonna prefer to keep these areas if in cover crops or in the fallow period. And when you have the fallow period or otherwise there's no crops there, you can use some things like that can help in the weed control, such as cultivation or the use of non-selective herbicides to control these weeds. And why is it important to control these weeds while you're in the fallow? It's important because you can achieve a better weed control during the vegetable production. So as I told you before, you can use the non-selective herbicides such as glyphosate, paraquat, and like some pre-emergence as flumioxazine. But most of this time, these herbicides are going to be applied as a broadcast method, and it's going to be applied in the whole area, even then you don't have the weeds. And weeds usually they're going to grow in patches. So in 2018, the University of Florida developed a smart spray that's able to identify the weeds and apply herbicides in real time. And today I'm going to show you guys the evolution of this smart spray and use it also for the fallow. So just to give an introduction, so this was, all the trials were done in the Gulf Coast Research Center by University of Florida. For treatment, you have glyphosate used in broadcast, but also the target. And you have the combination with a pre-emergent herbicide, because sometimes in the past works that we had, you can see that our savings for the post-emergence herbicides are higher when you have application of a pre-emergence before. So here is the 3 trials that we have. So trial A and B, they're done on the spring of 2024, and the trial C was done on the summer of 2024. So you try to find 3 different width densities for this trial. So on trial A, the maximum of the widths that we counted before the application was 140 widths. Trial B was 106 widths, and the trial C was 299 widths per square meter. So you have this difference, and you're also trying to see how the spray is going to perform with these different densities. So for this, we have the YOLO VX trained. I was trained with more than 9,000 images. And then here is how you have the controller on the field. So let's see if I can move the mouse or not. Okay. So here you have the speed that is coordinated by GPS, so I can see how my tractor is going. For the fallow period, I use 2.5 miles per hour. And also you have another things for the controller, but especially when I'm applying, I'm going to be used off when I don't have to spray anything. On is when I want the broadcast method application, and out is when I want the model be working in detecting the weeds. So as you can see, using the bounding boxes, on this time I was being able to identify what is a broadleaf, what is a nutsack, and what is a grass. But for the calculations of precision, recall, and everything, you not discriminate these weeds, because in the end I'm applying herbicide for everything at the same time, so I'm not using different herbicides for each category of weed. And here is how you have the system. So you have the computer that is inside of the tractor if they see, just because Florida summer can be really hot, so you're just really trying to avoid to damage this computer. You have the GPS in the top of the tractor that gives us better signal, and then you get the speeds. You have the control box of the computer, and you have, for this case, 2 cameras. Each camera is responsible for 4 nozzles. So left camera, the 4 nozzles here, and the other camera, the other 4 nozzles. And in this time we had 8 nozzles commanded by solenoids from T-Jet. So what do you evaluate on this time? You evaluate the width density, so you're trying to see if the target spray can give you the same width control as you have in the broadcast application. You had the width biomass, and also in every time that I was applying, I was comparing the volume that I was applying with the broadcast volume. So I can say how much of the activity ingredient I'm saving, how much this is from in the perspective of just the herbicides, not the keeping how much money the growers can save. And also for finalize, you also have the model accuracy in the field. So how I do this? So for the controller, I have the same access for the screen of the controller I have in the iPad, so I can record the images. And from these images, I can extract the frames, and from the frames, I can count how much weeds are being detected or not. So just to give you, I know that most of you is not weed scientists, so this is just for you to see that when you have the glyphosate alone by the flumioxazine, if the glyphosate on trial A was not that different, so the control was almost the same. But this is different when you go to the trial B. So what is the difference between them? So what you saw, that one has more nutsack, the other one has more grasses, and this can be a difference too. So sometimes flumioxazine in combination with glyphosate is going to give you better, a better control for different kind of weeds. So here is, so all the treatments, like when you have the combination, they suppress more the weeds compared to the non-treatment. And on trial C, that you have the highest weed density, you can see that you even had a correlationship over time. So it was the treatments over time that was giving you some results, but still the chemical treatments was better than the non-treatment. And here is the biomass. Again, it's just to show you guys that it's still like, sometimes for the trial B, the combination is really a thing, so it's gonna really depend of how is your weeds in the area. But you got for the part that I think most of the people is gonna be interested, like how much this is gonna be saving for my money, like is worth it for us to use the target application, is really like, is gonna work for the growers. So as you can see, if you're different with densities and different treatments, you have different savings. So here you can see like for trial A, you have just 20%, 27% of savings of the active ingredient we apply. But then when you go to the trial B, it's like 51%. But when you go to trial C, where you had the biggest weed density before, you can achieve 87% of savings. So, like for a grower, has 87% less herbicide cost is a big thing, but also for the environment, you're putting less herbicides on the environment and still having the same weed control. So here you can see also for the combination. So here was just with the glyphosate. And here we have the glyphosate combined with flumioxazine. So if you look, when you have just the glyphosate, you have the price that was the maximum like $42 per hectare. But when you apply flumioxazine, this price is going to be almost 200. This is because flumioxazine is an expensive herbicide. But still, if you're thinking as in the trial B, you have a better control when you're applying the pre-emergent. So sometimes it's going to be a higher price, but it's still worth for your control on the area. So, and still, if you're applying using the targeted spray, you still can have 54% of savings for these herbicides, but 62% of cost reduction. So it's still expensive, more expensive than just apply glyphosate. But in the order for a better control, sometimes it's better to have a little higher price. And remember that I told you that I record the images and extract the frames, and then I count every single weed that was detected or not by the system. So here I'm showing you how is the in real time the weed detection for this model. So because when you're training the computer, you achieve a precision more than 90%, but sometimes when you go to the field, it's not the reality. So you're really trying to see how is this on the field, and we got pretty good results. Here on trial B, remember that I told you that I have a lot of nutsack. So what happens sometimes, this nutsack is the one that's really easy for the model, sometimes miss it, because the leaves is really thin, and then sometimes it's really small. So you're working on to try to get better images or better resolution for the camera to get all these weeds. But it's still, if I'm applying a weed that's close to the nutsack, I still have the control, so for us it's still good. But you can see the precision, almost all the moments are 100%, and always like more variation also in the recall. So you have the maximum 20% of the weeds being missing, but it's still a pretty good result for a real-time application. And as you can conclude, so the combination of glyphosate with flumioxazine gives you the best weed control. The cost savings in average can be 55% for glyphosate and 45% for the combination of glyphosate and flumioxazine. And our model accuracy on this time was 90% of detecting weeds in real time. So for now with this, I really appreciate your attention. Thank you.
All right, thank you. We do have time for several questions, so yes.
Yeah.
My question is about the biomass amount that you estimate, and you vary the application rate based on that. How do you estimate the amount of biomass for the application?
For the weed biomass, you go to the field. So in that case, before I start this trial, I put my quadrants on the area, and they are fixed, if flags. So I don't, if you can see on this image, you can see that I have flags in the area. So this is my quadrants. For each point I have 4. So it's 4 replications. And even for the weed density or weed biomass, I'm always using these quadrants. So in the end of the season, I went to this area and collected all the weeds that are inside of these quadrants and harvested them and put to be on the dry chamber for 10 days. And then you have the weight.
So you don't measure on the wall?
No, the weed biomass is just the end, and between this period is just the weed density.
Thank you.
I may have missed it. The control system you were using, was that developed at the university? Or was
Yeah.
that- okay.
Yeah, it was developed in 2018, and now you're just get an evolution of them.
Got a follow-up related to that. So you obviously showed the cost reduction, but you know there is the additional cost of that system. Do you have any idea what the kind of the economic, where that break-even point would be in
So
terms
yeah,
of?
we didn't do like yet this really like cost estimation, but we have kind of how much our system worth it. So the computer is not more than $2,000, and if you put in 8 solenoids, 120. So in the total, it's not going to be more than $10,000 for this whole system. Yeah.
I wrote here a little bit late, but what's the computer that makes the variable grade application? It goes inside the track floor.
So first, it's not variable rate application. It's like just normal. So it's just open and close the solenoids to apply. So usually gonna have a buffer of 2 inches ahead and back. And the computer is an NVIDIA. Yeah, he can
explain later because I'm gonna present.
I see we got somebody else. Are you the next speaker?
Yeah, he's the next speaker.
Yes.
How fast can the system drive, and how does that compare to existing solutions?
So how fast? This was the maximum that we test right now, but we're trying to go to 4 miles per hour on the next applications. And the second part of the question?
How does that compare to existing solutions?
So compared to existing solutions, it's gonna be dependent. The vegetable system is gonna depend on the crops. But usually the growers is not gonna be more than 4 miles per hour. What you're facing right now is more like the difference of the pressure by the solenoids and the nozzles that you can express. So like the solenoids, the maximum that they can handle, I think, is 13 bar. Yeah. So, but like if you go to watermelon growers, they're gonna be applying on 300 psi. So this is just like some limitations that you try to solve right now. But until now, you're almost getting off the commercial ones, but it's not that much yet.
Final question. Yeah,
Okay.
no one needs
We missed a little bit at the beginning. So based on this slide, it looks like all your chart is based only has the wheat. You don't have any crops, and all the accuracy you report is not in the actual production system. I mean, for the wheat identification. Right?
Because it's fallow, so fallow you don't have crops.
It's pretty.
Okay.
Yeah, it's like for the fallow period, it's just the evaluation, how is the weed control without no crops. You have some works with crops because it's vegetable system, so when I have crops, I'm gonna have the bed. And then when I have the bed, I have to apply just in the row middles or in the bed top.
Okay.
So it's,
That's specific stage.
Yeah.
Okay. Thank you.
All right. Thank you.
thank you.
So, you wanna come on up? Said we've got another robotic spraying presentation. So this is Renato Fortunato, also from the University of Florida. So said choose the mouse to point and should pop up.
Yeah.
Yeah.
So good morning, my name is Renato. I am also a postdoctoral associate at the University of Florida, and we are working together with Smart Sprayer. And today I'm going to be presenting one of our research at the University of Florida that was targeted with controlling punch hole using AI-based Smart Sprayer. So basically, most of vegetables in Florida are cultivated using plasticulture production system, which means we have to prepare the soil and create vegetable bed. And we apply some products like fumigants and emergent herbicides, and we cover the vegetable beds with plastic mulch. And the plastic mulch can be different colors. And the problem is, when we apply the pre-soil fumigants and herbicides, we are applying before laying the plastic mulch. So we are using like herbicide in area that is not necessary, because the plastic will protect the soil against sun and other factors, and we don't have weeds like growing underneath the plastic mulch. But the problem is when 1 month later we are going to go to the field and create the punch hole to transplant the plant. So the punch hole is this part. So when we create the punch hole, we create opportunity to start growing the weeds. And remember, we apply the pre-emergent herbicide 1 month before, so we don't have the effects of the herbicides. So we came up with the idea of using convolutional neural network based on YOLO model, because like easy integration, we can like customize. So basically, we trained the model to be able to recognize different objects. In this case, the punch holes. So in this research, the objectives were we trained a YOLO model to be able to recognize the punch hole, only the punch hole alone, or the punch hole with the plants, with the tomato plants transplanted. So we deployed the trained model in a custom computer. We developed the computer, like not develop the components, but we create the computer and a graphical user interface. And we developed the smart sprayer, and we ran some experimental trials to compare the savings between non-target and target application. So basically, we collect the traditional way we create our model, everything. We go to the field and we record some videos. We extract the video frames to perform the annotation. So we collect different like days, different conditions to create a data set variability. So for example, we have the plastic mulch, like the vegetable bed with soil here, because we have this characteristic in the field. So we have water drops, sand, plant with punch hole with occlusion. So we have to try to simulate the real condition in the field. So we did the annotation using the bounding box. Doesn't matter if I have only the punch hole or punch hole with the plant. So we did the annotation in the bounding box. And our data set, we have a little bit more than 3,000 pictures and 3,000 annotations. The graphical user interface we created using PyQt5, OpenCV, and different libraries, open source libraries. We performed the laboratory adjustments. I'm going to explain a little bit later because we had to calibrate the system. We developed a smart spray hardware, and we conducted some experimental trials to see if our proposed idea is working, compared target and non-target application. So we choose YOLO V8X because at the time we conducted this research, it was the most advanced model we have right now, with P2 configuration 5. P2, which means we have an X output layer, because the traditional YOLO we have 3 output layers. So P2 we have an extra one that is optimized for small objects, so we have more chance to identify small objects. We trained the model a little bit more, 3,000 epochs. The way we conduct the model training, I overfeed this model. I use the same data set to train and to validate. So basically my metric is almost perfect because my test site is going to be the field. So I always try to overfeed the model as much as possible to be sure the model is accurate. So when I go to the field, basically my validation data set. So the fluxogram, so we have the YOLO V8X model trained. So we deploy on the custom computer based on NVIDIA GPU. We have different sensors, cameras, GPS model to collect the data. And the graphical user interface we developed, and the hardware as well. So the graphical user interface, we have 2 cameras. We can control 8 nozzles independently. But for this research, we are using a single camera and a single nozzle because we have a single line of punch hole. But basically, we can, each camera, each video frame, we have 4 vertical zones here, and each zone is we have like the correspondent nozzle. So we have 8 independent nozzles, and each camera is controlled in 4 sections. So if I have detection in the first section, the first nozzle is going to be activated. The third section, the third nozzle is going to be activated, all independently. So the second tab, we have the configuration, because we have to put the camera in position, we have to adjust the offset distance, and system latency, and a lot of parameters. And we can choose different modules, for example, to detect disease or whatever module we can train. And here, Anna showed you before, we are going to have the video frames in real time with the detections. But before going to the field, we have to calibrate the system, because we are measuring the object position on the ground based on pixel size. So I have to calibrate the entire system. So basically we have some parameters. For example, the camera offset distance to the nozzle, which means I have to calculate the camera, the center of the camera to the center of the nozzle. I have to provide this distance. So I found that 26 centimeters for this specific research was the optimal parameter. Camera height 45 centimeters because the camera is facing downwards to the target. Spray buffer zone 5 centimeters, which means I have the detection here, and I am adding 5 centimeters forward and 5 centimeters backward. So I have like a more chance to apply the product. Nozzle orientation 135 because I am applying the punch hole. Speed 5 kilometers per hour. And the system latency 0.05 milliseconds. Which means again, is the delay the system has to collect the video frame, perform the object detection, send the command to the nozzle, and apply the product. So we have to provide this parameter as well. And we are using like a conveyor, a small treadmill, so I can run like a train the model to identify the white dot. So I can run in the lab and adjust in real time the parameters before going to the field. So the hardware for the smart sprayer, we are using like normal security camera. We are using a global shooter camera right now because normally the cameras we have the sensor is a rolling shooter, which means the camera captures the video frame in lines, in sequence to create the video frame. In global shooter we collect the video frame in a single shot, so we don't have distortion. The computer is based on Mine ITX, running CPU Core i9. The GPU is RTX, NVIDIA RTX 8000, 12 gigabytes, and that I convert the model to TensorRT because it's faster and more efficient. But we are, with 2 cameras, we are using 35% of the GPU, so we have a lot of research. We have the GPS RTK just to track the tractor speed, to measure the speed. The communication between the computer and the solenoid is based on serial port. And we have a touchscreen display to be able to adjust parameters in real time. And the solenoid, right now we are using TJet as our actuator. So basically, like, this is the layout we conduct our experiment in the field. So the field we have 4 replicates. So we have 4, I think it's 12 vertical beds. So each replicate, we have 3 beds, if I am right, I don't remember exactly. But we have on average 244 punch holes. In the model, we're not able to recognize 34. And the success hit 210, which means we have the accuracy of 86%. And the initial herbicide savings was 84%, but this value is not correct, because since we have 34 nozzle punch holes that were not recognized, we are overestimating the value. So when we take into account everything, the final saving was 70%, which means we are applying 70% less herbicide compared to the traditional way. The problem in the field we noticed is due to occlusion, because since we have some punch holes that was like open without plant, and some of them with plants, we have occlusion, so the model was not able to see the punch hole. So this caused the problem. But we just did the test last week. I trained a ULV 11 medium size, with P2 configuration file, and we were able to recognize 100% of the punch holes. So basically, overcame this problem. And I did a little bit different because this model had a single class. So I trained the model using two classes, plant and punch hole. So it doesn't matter if I have only the punch hole or with the plant, I'm going to apply the product. So we just published an article a couple weeks ago. Unfortunately, I don't have time to explain everything about the code because it's quite complicated, but I try to explain this paper, so we have more description. But basically, we developed the entire system at University of Florida, so since the computer, the code, and the hardware, and we are conducting experiments in the field to validate this and compare it to the traditional way of applying products. At the moment of this research, 86% was in the field or like accuracy, but the good side, we were able to save at least 70% of the herbicide. It's less herbicide, which means less agrochemical in the environment, but for the farmers, it's like less cost to produce the plant, the main crop. And I just finalized this part. We are using the same controller, but we are updating the GPU, some components. Right now we are going to have 5 cameras running at the same time, a single computer and a single yellow model running multi-thread. So we are going to have 5 cameras and 20 nozzles working at the same time. Basically we have 5 sections, and each section we have 4 nozzles. So this equipment is for strawberry row middle application. Row middle is this space between the 2 raised beds. So we have 1 camera here and 4 nozzles here. So we have 5 sections, 5 cameras, 1 model, 1 computer, and 20 nozzles running at the same time. I don't have the results right now because I just finalized this smart sprayer and the season is over. But we are trying to develop a system that we can use for multiple proposals. For example, right now we are developing a watermelon disease sprayer. So we are going to have basically the same concept, but for different application. Basically, we have just have to train the model and adjust the hardware just to calibrate this part. So, well, that's it. Thank you very much.
All right, thank you. We do have time for questions, so open it up. Anyone has a question? Yes.
Thank you for the presentation. It was good. And actually, I have a question about the GPS. How the GPS works in this project, and you have used RTX GPS, right? Yeah. So, did you use the GPS subscription, or did you use the base station for the GPS? And how much accurate it is?
No, but the GPS, we just replaced it to RTK because the future we are going to create a map in real time. Because since we have the detection, we can convert the bounding box to real coordinates. But we don't have base station anything, just to track the speed.
Okay.
Just like the sensor to be able to measure the speed.
Okay.
And not to use for that.
Thank you.
Yes, in the back.
Yeah, really cool work. I have a couple of questions here. First one is, which model of the Jetson did you use?
No, we are using normal GPU. It's a normal mini RTX computer. It's RTX 8000. Right now we just switched to RTX 4060, the GPU computer.
Okay, I think one of your slides you showed you actually have a Jetson system.
No, I'm gonna, let's see.
Yeah, you have it right here.
No,
okay,
this, sorry,
I
yes.
missed it. Okay, I thought you had a Jetson.
No, this just a random example. Yes,
Somebody's picture, right.
because if it's good, yeah.
So, and then I think you also showed your nozzle is actually out a 30, so it's not completely used as a.
Yes.
The next one.
Yeah, this one is better. Or maybe this one. Yeah, the nozzle we apply like the angle to avoid applying product in the plant. So we are trying to apply on the punch hole, so it needs to be angle. because the goal is to control the weed in the punch hole. So if you put the nozzle like facing down, we are going to apply the product to the plant. So we have to apply vertical to be able to reach on the punch hole.
And then how fast?
Oh, let's get one more over here, and then we'll need to move on. So yeah, you
When you're applying at an angle, how do you make sure if the plant is there, it doesn't spray on the plants?
Sorry, say again, please.
When you're applying at an angle in a punch hole which has plants, do you have something in the code or some
No.
which makes like stops it from applying it and spraying it on the plants and
No, we try to do this physically, so we are gonna apply. Eventually, we have some product that come in contact with the plants, but the product is selective, so we can apply in the plant. We don't have injury, but we try to avoid. But like, we don't have anything, just applying whatever condition.
All right. Well, we need to move on. So if we've got more questions. We can chat after the session. So our next speaker is Anayat Rasul from South Dakota State. And again, we.
So herbicide is going to be selective, but it's still sometimes kind of poor. Yeah, so like you're trying to avoid the fact that you can, and you're trying to avoid them.
Anayat Rasul from South Dakota State. And again, we're looking at more precision weed management applications. So.
Good morning, everyone. I am Inayat Rasul, grad student at Machine Vision and Robotics and Lab, and today I am representing Biosystems and Agriculture Engineering Department, South Dakota State University. Today I will be representing on the topic real-time weed detection, canopy area estimation, and variable rate herbicide application using a ground vehicle. Soybean is one of the most important cash crops in South Dakota and in the whole Midwest region. As you can see in the map by USDA, that soybean is a major crop in a major states of United States of America. Sultani et al. Performed a study to see that what is the potential loss in soybean yields if weeds are not properly managed. A total estimated $16.3 billion loss can happen if weeds are not managed only in United States and Canada. The bar over there in yellow highlights South Dakota and an estimated $800 million potential yield loss due to improper management of weeds. South Dakota State University Extension, they performed a survey to check what is the most preferable method of weed management in South Dakota, and by far herbicide application is the biggest practice used, around 37%. But with herbicide comes different problems as well, and it is multifaceted, not just a single faceted one. One being the financial burden. At each acre, around 7.8 kilograms of herbicide is applied. That's not all. There's also, we are losing our precious soil. Montana State University Extension, they performed a study to see that they looked at glyphosate only, that if the concentration of glyphosate is more than 5 parts per billion in soil, that leads to improper germination or even death of plants. We also have studies in medical sciences which say that if glyphosate makes its way into our human system, it can lead to respiratory disorders, neurodegenerative disorders, reproductive disorders, and immunological disorders. So these are critical problems we need to solve. And with the advent of robotics, computer vision, and powerful edge computing devices, people are trying to develop solutions which are precision-based application. They are becoming more popular. As you see, a presenter before me, a great project, they are working on it, and it is still in earlier stages. Here you can see a robot which uses weed technology, so it detects weed based on computer vision and then shoots laser to kill it. There are people who are working with mechanical removal of weeds. There are people who are using spraying. For example, here you can see a tractor which can spray. But these are still very new, and they are spot spraying. So we chose spraying right now because it is already accepted and trusted by farmers, and the fundamental infrastructure is already present. So there is low initial cost, and it can be adopted very easily at this moment. The companies which have already developed, they are closed source. So we have wanted to develop these things for open source and academia. The proposed solution is combining spraying with deep learning based computer vision models to transform traditional blanket spraying to smart precision spraying. Camera captures the images of the weed in real time, and deep learning based model, YOLO 11 in our case, can detect weeds and estimate its canopy area. So we are doing variable rate based on canopy area and spot spraying as well. For precision, then precision controlled sprayer nozzles can be triggered to apply the product. The overall goal of this objective, we started this project just like few semesters ago, and it is to develop a robotic smart spraying system capable of optimizing herbicide application efficiency while significantly reducing chemical usage and actually killing the weed. Objective at this point was to develop AI-driven robotic spray system for real-time variable rate application based on weed canopy coverage area. Here you can see the assembly of the system. It is based on FarmNG's Amiga platform, to which we added our own systems, embedded control units, the sprayer boom assembly, so on and so forth. And you can, due to time constraints, I cannot go in detail in each component right now. For any robot to be smart, it must have a brain where it processes everything. This is our embedded control unit, which is based on low-cost NVIDIA Jetson Ori Nano, microcontrollers, switching modules and relays, and we also added a display mode there for real-time debugging and real-time parameter tuning as well. This is the schematic of Boom. We chose 2 cameras and 4 nozzles right now. So this nozzle one camera can control multiple nozzles. And this system which we developed, the algorithm, it can handle more than 1 camera as well. This tells us that it is scalable. Due to a small computer and at a test stage, we just chose 2. It can be scaled up to handle more cameras and more nozzles in the future. We chose 0.508 meters distance, which is standard right now. And here are the specifications of the components we use. We use RDOCam USB camera, TJet nozzle body, TJet control solenoid valve, and TJet nozzle tips, which are generally used in herbicide application. For any robot to be smart, it must have a processor system which can get an idea of what's its environment. And ours is based on YOLO 11, which is a very popular algorithm. And here you have the architecture of it. It is based on, it has backbone, neck, and head. Backbone utilizes convolutional neural networks and extracts the low-level features. Neck gives the context to those features, like scale context, and head is responsible for the detections. It is one shot, the image comes in, and we have the detection. This is how we got started. So first of all, the image acquisition took place in controlled environment where we conducted this experiment at this stage. Then those images were annotated using RoboFlow. We trained the model and then we finally deployed it on the robot. Here you can see all the data split and the number of epochs we used. Precision recall and MEP50 was used as our metric for performance tracking. Here is an example of how our deployment looked like. We have a detection over there with canopy area estimation as well, and these lines you see are related to when to spray and when to not spray the product. This is the control logic. As I told earlier, that we have our camera and 2 solenoid valves in the middle, and first of all, the control logic takes place, like image acquisition takes place. The AI model, detection model runs to detect whether we have weed or not, and then a decision is made at this stage in real time. If you don't have weed, a signal is sent, a string is serially sent from Arduino Jetson to the Arduino Mega, to NVIDIA Jetson to Arduino Mega. OFF pound \n means turn off that nozzle. But if we have a weed detection, then the cropped images pass through the canopy area estimation or segmentation model to see whether we have a small canopy area, medium canopy area, or large canopy area, to which we have a PWM value mapped to it, and then a message is sent on pound asterisk backslash n. Here pound means nozzle address and asterisk means what is the level, PWM level to apply there. This was the experiment layout between two guide tapes, and this guide tape was, distance was decided based on the track width. The plants were kept and the robot was run. And water sensitive paper were put on the side, and I'm not sure whether the spray is visible or not. The spray was applied to those weeds. Then those water sensitive papers were collected and they were scanned using commercial scanners. Here are some results. So YOLO 11 detection result. You can see the precision, recall, and MAP50. These metrics improved as the epochs increased. Almost 98.9 MAP at 50% confidence interval was achieved. Almost all of the weeds were correctly classified, and there were some misclassification of ground as weeds. So this is a very good performance on the detection side. Here are the results for our segmentation model. The performance here is not too good. It is acceptable at this stage, and this can be attributed to poor annotation quality of segmentation masks. Then all those water sensitive papers were analyzed to see what are the spray coverage and what are the number of small, medium, and large droplet sizes, and then a distribution was plotted, and also a heat map was plotted to see at a particular stage, at a particular space, how many droplets, what are the number of droplets at that position. Then the coverage area was plotted for small, medium, and large, and box plot was plotted. For each classes we had 5 plants, 5 for small canopy, 5 for medium canopy, and 5 for large canopy. Overall, we see increasing trend from small to large to medium to large. That means the smart sprayer can spray at variable rate. But we see a lot of variability in the medium canopy area, and that is attributed to, again, the poor performance of our segmentation model. So the segmentation model confused a lot of medium-sized weeds as small and some of them as large, leading to sometimes spraying at higher rate and sometimes at lower rate, which resulted in so much variability. What are the key takeaways? YOLO 11 based custom deep learning model was able to detect and estimate canopy area of the wheat plants. More work needs to be done so that the segmentation performance increases and it can be ready for field trial as well. And the system is able to spray weeds at different rate based on the canopy area. Future work, more rigorous testing of the system with water sensitive paper. Testing the spraying system at different speeds and weed species commonly found in South Dakota like Palman thameri, ragweed, pigweed, etc., and determining optimum PWM corresponding to a canopy size to kill it and then perform field trials. I'd like to thank all the people who helped throughout this project, Brian, Hassan, Dr. Hassan, and the rest of the MWAS team. I'd like to thank South Dakota Soybean Research and Promotion Council, USDA, and NIFA. Again, extreme gratitude to the whole MWAS team, and I'm open to questions now.
All right, thank you. We do have time for questions, so I see one right there.
Okay, thank you for your presentation. And I have seen that you have used the Amiga. I guess there is the brain with the Amiga, and you have developed your own brain also.
Yes.
So did you use the PharmNG Amiga's brain in your project?
Right now we have not used PharmNG Amiga's brain because if you want to scale it up, we don't want to be limited by the hardware Amiga guys provided. And also we want to test it with already present implements with the farmers as well. So we want our spraying system to be independent of Amiga. But we will use Amiga, we eventually want this PharmNG platform to be autonomous. So we'll use it for navigation because the PharmNG Amiga proprietary brain provides good communication with the wheels because it is based on CAN. And if you want to control that without intelligence system they provide, it's a bit difficult and you have to hack into the communication.
Thank you, sir.
Yeah, right.
So how big is considered to be a large canopy like the weed, and how small you consider the small weed?
Yeah, that is a very good question, and this is a part of our future work. So right now, based on visual inspection because we wanted to do a concept test. So, okay, this looks like big to me. Then I took it to the segmentation model and I noted down all the big plants which I thought that are big. And based on that, I did the thresholding. We need to work with other lead scientists to know for each species what is the big size, what is considered big, what is small. And when the PWM study in future, I said like, okay, at this, what should be the spray deposition to actually kill it? And we need to collaborate with lead scientists and we are open to it.
Good answer. Okay, yeah, I know you had.
There's some related goals to the control unit. I see you have used the force supply, which means you're supplying the bigger using AC source.
Okay, so here you can see the power pack.
Yeah.
Again, we developed this for another system where we had AC system there. And we use that to transfer it. So this power pack is independent. Again, we want it independent because we are testing it on other system as well, other robots as well. So this power pack is independent of the Giga supply and it can provide AC as well. So we have AC and then this power supply converts it to uninterrupted power supply to the robots.
So what about the GPIOs and which used? So I see you use the Arduino board to control the sprayers, like the relation actuators. Why didn't you use like GPIOs of the edge devices?
Right now, so that it looks good. One of them is that wire routing problems. And because Arduino has a lot of support, more support than the GPIO in Jetson. And we did not see too much latency drop. If we see in future, we might go with another route. Right now, it was fast, it was real time, we saw it, and because of the support the Arduino framework provides, we went with Arduino.
The communication was based on your somewhere.
So yeah, serially, the communication between Jetson and Arduino is serial.
Okay, one more question.
So I was late to the presentation, but the nozzle, kind of nozzles, is it a standard flat fan or do you have a specialized nozzle?
Yeah, so it can be changed again based on like there is a proof of concept right now, and based on what weed or what product we are applying, we can change the tips. Right now we chose a flat tip. Here are the component specifications.
One thing, we are also working with Jetson AGX, and we try to utilize the GPIO pins to control the actuators and other stuff. But what we found out is that it's really tough to like, and the GPIO pins works as input, but cannot like submit the comments to the other motors and other stuff. And we contacted with the NVIDIA as well, but they give us a proper solution for that.
So that might be another, that Arduino might work.
Yeah, got a lot of good hardware discussion. Y'all continue later. So we do need to move on. So our next presenter is, we're going back to the University of Florida. Good job. So Vinay Vijay-Kumar from the University of Florida, and we'll be talking about an autonomous smart sprayer for precision weed management in vegetables. So, an updated version here. Let me remind everyone, there should be some QR codes floating around the room. Does anybody see those?
So the QR code is for the survey, right?
For the survey.
It doesn't work.
I'll have to get on the survey.
I've been trying to fill up and it just doesn't open the.
Well, I hope they'll probably have something up at the luncheon, so please do the survey. And if you've got yours up and you're ready to go, then all right. And like I said, I ask that you use the pointer on the mouse. You can advance with that if you want, just so that you can, so anybody remotely can view.
Okay, hello everyone. I know you already had 3 weed sprayers. I'm I'm going to put one more onto you.
Last one.
Please don't get bored. With so many weed sprays already existing, you might think that all the weeds are probably dead, at least in Florida. But that's not the case, because weeds are immortal. They don't die. We try to control them at least. So yeah, my name is Vinay. Completed my PhD from University of Florida. And my work was on developing the machine vision and spraying system for the robotic smart sprayer. And today's topic is AI-driven robotic smart sprayer for precision weed management in vegetable production. Yeah, so we know the problem. I think you have seen it many times. There's a lot of weeds, causes environmental problems, takes away resources from the plants. So we want to kill them, but not harm the environment and not harm the plants. There are some existing commercial technologies that are for different crops. So we wanted to develop one for the Southwest Florida environment for raised plasticulture beds, which can tackle 3 weeds: sedge, broadleaf, and grassleaf weeds, and work on beds with tomato and pepper plants. Our target was to have a robotic system that works on the bed, the raised bed. It can spray on the edge of the beds as well as in the row middle. So I'm going to present this in 3 different sections. The first one is the machine vision system, the second is spraying system, and the third I'll go through the way the whole system, the prototype was built, and the final testing results. So in the machine vision system, we have a industrial camera from Daheng, Get Camera. We are using that and a U-Blox RTK GPS. We get the data on a Dell Alienware 16 laptop with a NVIDIA 4070 GPU, and we send the message to the spraying system, which has one microcontroller which controls 16 nozzles, T-jet nozzles, flat fan, narrow cone, and another microcontroller which is used to control the control elements, which will come to later on, and also maintains the pressure in the nozzles. Right now we'll just go through the first part, which is the machine vision system. Yeah, so the objective of the machine vision system here were to work on the improving the detection accuracy, as well as making sure that the speed in real time was good. Because it's a real-time system, we have to have a careful balance between both. So those 2 were the major objectives, and the minor objectives were, while developing with this robot, we wanted to make sure that the hardware that we have is robust enough to work in the extreme heat, humid climate of Southwest Florida, and also the software should be good enough to work in that and support the hardware. So we collected around 2,000, more than that, images over a period of time, different calamity conditions, different seasons. We trained it. The initial data set had too much of a bias towards broadleaf. I'll come to that a bit later as well. And this number of sedge and grass were less in terms of the number of instances as well as the number of images per class. So it was required to augment the data set, especially to do a class-focused augmentation for the sedge and grass, because we want a better representation and a better balance of the data set. So we did temporal augmentation and random size crop with bounding box, and then I trained it on YOLO V8 nano model, and I implemented a multi-threaded code which takes in input from the camera and the GPS, while running it and doing the processing using YOLO V8, getting the frames back, getting the nozzle zones back. So like I mentioned before, I have 16 zones in this robot, and based on the location, of the weed, I get the nozzle information in terms of the zone, and I send it back, and then we send it to the spraying system, which then triggers the appropriate nozzle belonging to that zone. After training it in YOLO V8, the detection on the training set and on the testing and the validation set, actually it's on the test set, the performance was more than 80% for weeds, close to 98-99% for plants. There's no overfitting here, but broadleaf performance was not that great, and one of the reasons is that in the field you see too many varieties of broadleaf. It's So in this image you see these 6 varieties. So cursor. Okay. So see these 6 varieties. Yeah. Okay. Fine. And when you try to add more classes for individual variety, the whole total number of classes of the total number of images of these specific classes broadleaf also increases. So again, you have to find a fine balance for this. So because of this large variety of broadleaf, the performance came down. Sedge and broadleaf, sedge and grass also had a little bit of an issue because of similar leaf structures and stuff. But however, the performance was acceptable, I would say. Moving from detection to the speed, converted the model to a TensorRT form, and for the code's real-time implementation, the FPS of the code after converting it to an FP16 floating-point 16 version was 20 to 25. From my experience, if you have it more than 15 FPS, it is very good for, at least manageable for a real-time operation, and for our system we got it to 20 to 25. Now let's move on to the spraying system and controls. So in the previous figure I told you about the subsystems. Now we are going to talk a little bit on this part where we are going to be controlling the control element to make sure we have to maintain set pressure. And there were a few tests which are done based on the nozzle height, the number of nozzles, the types of nozzles, as well as the pressure, and based on that we got the results that between 15 to 20 psi we get a good spray which is less, I mean less wide. We don't want to spray it, we don't want a large cone angle, we want a narrow cone angle, and we also want to maintain the pressure so that it is not affected by drift. So based on all those conclusions, we had to develop a control system which could maintain the set pressure. So from the nozzle section, based on the conclusion, we can control the either the pumps or the control valve or the proportional control or both. So in this case we decided to control both, and we have a PID controller which individually controls the pumps. So we have 4 pumps in the system. I'll come to the spraying layer of the spraying system in a minute. And we have 1 proportional control valve, and both of these work in tandem to make sure that the pressure, either 15 psi or 20 psi that we found out through experiments, is always maintained during the real-time operation. This is the layout of the spraying system. You can see we have 4 pumps here which take in the herbicide from the herbicide tank, goes to the main pipe where you have 16 nozzles. There is a pressure gauge at the input, there is a pressure gauge at the output. For monitoring, we also have a pressure transducer and a proportional control valve. The pressure transducer gives real-time input to the controller, and we control, based on this input, we control the proportional control valve as well as the pumps, and then try to maintain the pressure for the real-time system. So after putting everything together, we are ready for the assembly and for the test. So now the third part is building the prototype. So we went through a couple of versions of prototype, and we built everything from scratch at Southwest Florida Research and Education Center. This was the first stage where it's made of aluminum extrusions and a wheelchair motor which drives it. I was using Jetson NVIDIA NX at that point. And the second prototype, I replaced the fixed wheels with caster wheels and added a bit more electronics. But again, we had, because of the soily, the sandy terrain of Southwest Florida, we had a lot of issues. So we had to overhaul the whole thing, and then we dismantled everything. We tried to make it bigger and put a better system together. Now, here you can see we put the 4 pumps. Now, in the second level of this prototype, we have the electrical and electronic systems. So we are using 4 pumps for that. You have the drivers. We have the 2 different microcontrollers over here, and a bunch of circuit breakers for added safety. Then in the stage 5, we put the solenoids, we put the motorized wheels. The motorized wheels are from UE Motors. They're quite cheap and easy to use. And these wheels with 16, these motorized ones with 16-inch wheels work very well in the sandy terrain. Once the motorized wheels were put together, we tested the robot on different terrains, grass, tar, then concrete, soil. The movement was reliable, the movement was good. Once the testing for the terrains was done, we fixed the camera. So this is the industrial camera. At that stage, we will use one industrial camera. So this hood covers all the solenoids and the piping system to prevent it from extreme heat and humidity and stuff. Once the camera was fit, we went on to real-time testing. So for testing, we did testing on tomato beds, pepper beds. So this is test 1, test 2, and for test 3, here we tested the performance on the edge of the beds. On these 2 tests, the performance was evaluated on the top of the bed, where we count the spraying performance in terms of how many correct targets were sprayed, how many were partially sprayed, how many were missed, stuff like that. Here, because it's more broadleaf dominated, which grow in patches, it's difficult to separate them and tell them that okay, we have 1 broadleaf or 4 broadleaf. So here we did in terms of zones, we did divided into 5 zones varying with different intensities, and we evaluated the performance based on that. For the test 1, we evaluated how many targets were sprayed, how many were partially sprayed, how many were missed, how many were not sprayed, and how many plants were sprayed, because it's important to know if we missprayed on any of them. So we got good results in terms of precision and recall of the spraying performance. Mind you, it's not the detection performance, it's the actual spraying performance. The detection performance was higher than this, but when you get to the spraying performance, there would be a lot of latency, there will be loss of communication. You have to take care of that, and after doing all that, we got a performance of 89% precision and 86% recall for test 1, which is on pepper beds. This for test 2, the same parameters. We have got a precision of 88% and a recall of 84%. Again, no plant sprayed on each of these tests. This is the test for the spraying zones, where instead of counting the number of targets sprayed, we focused on the area, the percentage coverage. The performance in the medium and high zones were good, while in the low intensity, the low density zones was a bit less because of the camera position where we have placed. And the early stage, when we were testing, it was like really early stage weeds, so we had a bit of issue with that. So going back to the summary, yeah, so the detection performance was good, the spraying performance was good for the pepper and tomato beds on top, and for the edge of the beds. On the low zones, it was slightly off. I want to show you a video. For some reason, I can't play it.
Just because of the pointer? Yeah. Okay. You get off the pointer mode.
Okay, nice, thank you. So this is a working video on the tomato bed, and here you will see a metric. Yeah, green means on target, yellow means imprecise spray, red is missed spray. So within the code itself, we have a limitation which makes sure that we don't spray too close to the plants. So if there's a nozzle zone where the bounding box says, okay, there's a weed here, but if it's too close to the plants, we don't spray there. Okay, let's move on to the pepper beds and the edge of the beds. What's the next slide? Yeah, okay. So this is a smaller video for pepper beds. Sorry, the brightness is not that high for the pepper. Okay, I'm going to show you a little bit of the edge of the beds, and here you will see. Oh shit.
Yeah. Spray inverted. We're going to need to wrap it up. So,
Yeah. Okay. So you will see it getting similar to you, but you will see it spraying on the edge. These edges in this side and that side, and it's a tricky place to spray. And because of the constraints of the camera position we had to move it to one side while spraying. I'm sorry, I don't know why it got rotated, but yeah, it is spraying somewhere. Yeah, but it's
yeah. All right.
Okay, so let's move on.
Let's
Yeah, so
wrap this up here.
sure. Yeah, that's it. Thank you for the.
All right, and if you got questions, we can visit with the speaker later. So let's, our next speaker, we have two now. We're moving on from weed spraying. So we've got one on detection and removal of plastic contaminants. And so Salvador Rock from Mississippi State. And I think we may have had some connection issues in here. You might not have had a good Wi-Fi signal. I know I walked out in the hall and it seemed to work there for me. I'll pass it around again if anyone needs that. Try it, hopefully. If not, if you don't get it to work now, then just do it after our session. So get yourself. All right.
Hello everyone, I'm Salidur Rahman and I'm doing my Master's in Biosystems Engineering at Mississippi State University, and my supervisor is Dr. Hussein Barakani. So I have seen that lots of people today talked about weed management system, but I will talk about a different topic. That is, I will talk about like managing the plastic bags in the cotton field. So my research is about detecting and removing the plastic contaminants from the cotton fields using the AI and robotic systems. So at first we want to know that why we want to do it. So we know that cotton is an important resource of fiber in the United States and it's a leading cash crop. So we want to keep the cotton production to a high note always. But the plastic contaminants, it can create a big mess, like it can disrupt the production of the cotton. Like when some plastic contaminants like get entangled with the in the cotton field with some cotton plants, it can like when the farmer goes to harvest the thing, he uses cotton picker, as you can see in the picture, or something like that, and the cotton picker tries to pick the whole cotton plant from the field. And like if there is any plastic bag in the field, plastic bag in the cotton plant or something like that, it actually get entangled with that thing, and there are some blades in the cotton plant. There are some blades in the cotton picker, so that plastic bags can actually get torn in hundreds of pieces. So that thing actually makes the whole cotton module polluted, and at last, if we want to make some clothes, shirts or t-shirts from that, that shirt or t-shirt may actually include those plastic bags, and actually it will decrease the rate of that thing. And we have estimated that economic loss is almost around $600 to $750 million, which is a big amount. So we want to deal with this thing, and we have found that the main sources of these plastic contaminants are like round module wraps, the plastic bags, and then mulch wraps in the fields, and also some plastic bottles. And it can also do some environmental damages, like it can damage the whole soil health. So for that thing, we want to create, we actually wanted to see the actual scenario in the field. So we actually went for collecting the real data, and we actually visited 3 different fields in Brooksville, Mississippi, and we have found 57 real plastic contaminants in that field. And we found that the plastic contaminants are more dense on the roadsides, and also like around half of them are. Is the pointer visible? Okay. Is the pointer visible?
So the pointer Yeah, if you go out.
Okay, so from this picture you can see that like most of the most of the contaminants are like entangled plastic bags, and like some of the plastic bags are also on the ground. But like we have also found that like 10 or 11% of those are from plastic bags or plastic bottles or cups. So for this we want to deal with this situation, and we have proposed a solution for that. That's a collaborative UAV UGV robotic system. So we will have a UAV in our system and also a UGV. So the UAV will actually go to the field, and it actually takes some pictures of the hotspots of those plastic contaminants in the field, and it sends some signals to the UGV, and UGV will it will navigate autonomously to the field and like pick those plastic contaminants from the field. So like this is the like workflow of the whole system. So you can see from here that first the UAV will fly to the field, and it will like capture the pictures of the plastic contaminants that is on the rows, and then it will send the RGB images to the object detection model 1, which we will have on the UAV platform, and then we will make a path planning algorithm from those object detection things, and then we will send the path planning algorithm to the Amiga we will have as our UGV system, and then the Amiga will navigate to the first contaminant location, and then it will have another object detection model there. So using that thing, it will like detect that is the plastic contaminant is entangled or is on the ground, and then it will use a depth camera which we use there, and then using that thing it will like predict the exact location of the plastic contaminants over there, and we will have a robotic arm and also an end effector attached to the UGV system, and then that robotic arm and end effector will pick those plastic contaminants from the cotton plant or field from there, and then it will navigate to the second system, and our system will like work on this workflow. So for that things, today I will actually talk about the both object detection models. I have worked on these things. So like we know that creating any object detection model requires a good data set. So for that, there is no available data set for the plastic bags so we actually try to create the whole data set. So for that system, we are working on our autonomous vehicle, that is the Amiga, but for that we have actually created a prototype of that system. That's a mobile platform, and we have recreated the whole the system we saw in the field, the plastic contaminants things, and using the mobile platform we built up, we actually captured images of those plastic contaminants, and for this we have, for the vision system, we have used the Luxonis OB Pro PoE camera, and also we have used the NVIDIA Jetson AGX Orin as our computing module, and we have taken pictures at 3 different angles and in different days and in different fields to create the dataset more diverse. So here you can see some of the comparison of the images we have taken. The images are taken in 125-degree angle, at 135-degree angle and 145-degree angle, and we have analyzed that the 135-degree angle gives us the best view of the field. Using that thing we can detect the plastic bags more easily, and using this thing we have trained our first object detection model. That's for the autonomous vehicle, that's the UGV. And we have actually used the 135-degree angle, and we have used 130 real plastic contaminant images we have captured from the images, and we have two classes here. That is the plastic bag mulch wraps that contains any entangled or grounded plastic bags. As you can see from here, one of them is entangled with the cotton plant here, and the other class is the we have annotated is other trash, and it contains any plastic bottles, cans or cheese bag, etc. And we have splitted the data set into train, test and validation set, and we have also performed some image augmentation like flip, rotation, and we have increased the brightness. And using this data set, we have
trained our object detection model. We have used the popular YOLO object detection model, and we have worked on YOLO V8 model. And after working with the hyperparameters, the learning rate, epoch, and image size, we have seen that the YOLO version 8 model actually gives us the best result. As you can see that the minimum average precision we got is 86%, and using this model we can almost detect 82% of the plastic contaminants in the field. And here are some inference images you can see from here, like the plastic bag mulch wraps, and these are detected correctly. And here's one of the big challenge here is that the plastic bags sometimes are more similar to the cotton plants, and they are not always accurately visible. So this was our main challenge. So we tried to work with this thing, and we got this result finally. And also, as I have said that we will also have a UAV platform in our system. So for the UAV, we will also have an object detection model there, and also we have created we have taken some images using our UAV, and we have created the multispectra and both the RGB images. Or for the RGB images, we have taken almost 1,000 images of that, and the image resolution was very good, 60 megapixels, and we have used the Skyfish M4 model for taking the images over there. And the images were taken from 50 and 30 feet altitude separately. And for that system, we have also trained the object detection model too. And for this one, we have tried with this model separately, and we have also navigate through these hyperparameters like batch size, epoch, learning rate, image size, and we have also found out that the small version of the YOLO V8 model actually gives us the best result. The mean average precision here is 76%, and using this thing, we can detect almost 80% of the plastic contaminants in the field. And this object detection is actually 30 feet altitude. And we have actually also two classes here, the plastic bag, mulch, wraps, and also the other trash. And here you can see some of the plastic contaminants detected. Here some I can't zoom here, but the blue rectangles here actually tells that there are some plastic bags available there. And in the left picture also, we are working on this thing, and it almost detects all the plastic contaminants in the picture correctly. But here you can see that there may be some defect here, so we are working on this thing. So we will work future more for refining this model, and our future work will be developing a robotic arm and also an end effector for handling the plastic contaminants with the UGV, and also we will develop a data transfer system transfer the signals from the UAV to the UGV, and also we will deploy the developed hardware and software models, and we will conduct the lab and field testing for this one. And so it was all for me, and I want to express my gratitude to Cotton Incorporated, USDA, and for their funding, and also the continuous support from AAI, and my team members, Asifur, Ashan, Mustafi, they also helped me on this project. So thanks a lot to them, and yeah, thank you everyone. If you have any questions.
All right, we've got time for some questions. So go ahead.
You have multiple types of plastics in the field. You have mulch, you have plastic bottles and stuff, and you have used two labels. One you have clump, what you know, and one you have your saying other trash. Wouldn't it be better if you have multiple classes for all of those trash, because that would be helpful in what sort of end effector or what should be the strategy of pulling it out, because mulch entangled in the plant, it might be, you might use a different approach to pick up a plastic on the plant.
Yeah, that's a good point. So for the UAV, our plan is to keep the classes in two separate types, because for the UAV, our target is to detect the locations of the plastic contaminants. But for the UJV, your idea is very good that we can separate the classes in 2 or 3 or 4 more types, that to know that the plastic bag is entangled or is on the ground. So we can work on that thing in our future prospect. Yeah, thank you for the question.
More questions? Yes, in the back.
How three questions, but like.
Let's just do one.
Yeah.
In case anybody else wants to ask one.
You're going to use UAV to detect the, polythene bag, right?
Yeah, exactly.
So are you going to use before defoliation or after defoliation? Because that should be a big case if you use UAV to detect the polythene bags in the ground, right?
Yeah, that's a good point, but as you know that our goal is to detect and remove the plastic bag before the harvesting time. So like if we can detect the plastic bags just before the harvesting time, that would be great, because you know that if we detect and remove the plastic contaminants before the defoliation, and after that it can happen that there may be more plastic bags over there. So then, if the cotton picker goes there and try to pick the plastic bags from there, then it can be problematic again. So our goal will be to detect as late as we can.
All right, thanks. One more question if anyone has one. Not, we'll go to our final speaker, and we're going back to robotic arms. So we've got Syed Soma Ben Severe from Cornell. So, yeah. I'll let you pull that up. And like I said, this will be our last presentation. So that will start.
So just by removing the cursor here, I can have that too? Or how
So
does it-
if you right click and you go to pointer options. Switch it back on.
Hi everyone, I'm Osama. I'm doing my PhD from Cornell University from Biological and Environmental Engineering Department. My major is on the soft robotic arms for agricultural operations, and today I'm going to share about kind of a narrative of how and why we need to use soft robotics in agriculture application and what are the challenges associated with their usage. So first thing, we know why robots in agriculture. That's the fundamental question. So it has been estimated that by 2030, the global food consumption would increase by 60%. I mean, we are not going anywhere there for the labor issues and all that stuff. So if we won't introduce automation and robotics in this industry, there would be a huge food shortages and supply chain things. So first, that's why we need to use robotics and automation in that. Then it comes to labor injuries and things associated with laborers working in the field. So when a machine is deployed, that is reduced significantly. And then of course, it's a highly efficient thing because of the repeatability and the same results which we get by using the same machine. So we come to conventional robots. We have seen a lot of people working on UR5 and these kind of robots. They are perfect. But they're perfect when it comes to R&D effort. Whenever you want to make something from lab to outside in the commercial field, you need something which can be easily scalable. So for example, for the reference, the UR5 arm, which has been heavily used in the academia, it costs around $45,000. So it's very good for R&D, but if you want to scale it for a commercial solution, there are significant challenges. The other thing is then when you're using fixed and rigid robotic manipulators, there's an issue of singularity. So you see there's a mathematical path that exists which a robot can follow because mathematically it exists, but because of the joint constraints and the geometry of the robot, it is impossible to follow that. So these are the things which makes the usage of fixed robots in agriculture tree fruit operation a little bit challenging. So a promising alternative for that is soft robotics. First, they are scalable and cost effective because of the material that is used for their fabrication. They are more dexterous, less singularity, and then they are safe for humans. Now, so we have found a solution, and then we know that there is a problem associated with the solution. So soft robotics, we know that, okay, yeah, that's the way forward, but there are some inherent problems associated with that. The first is that they are non-linear in nature. They have sag, they have flexibility, and that may induce difficulty when operating. The other thing is the sensor and the proprioceptive stuff we use to get the feedback of the robotic arm. Conventionally, we use encoder optical based or disc based and what's another thing, Hall effect based sensor for getting the joint angles. But when it comes to soft arms or anything related to soft robotics, that cannot be deployed for positioning there as easily as it is being done in the rigid robotic arms. And then when it comes to non-conventional sensor, the control system of the system becomes more complex. So now coming to what I am doing, my first thing, like my objective is to develop a machine vision system to address the non-linearity that is associated with soft robotic manipulators and to perform precise tree fruit operation, that is either food harvesting, and in fruit I mean apple for my use case, and flower thinning. So if I would cut down the tasks which are associated with my primary objective, the first is I have to estimate the detected object and get the detect and then estimate the distance of the object, and then the other is to perform the manipulation. So that's kind of like a workflow. It starts with detecting an object, which in my case is an apple, estimate the distance in 3D, lock a particular distance because there can be many apples, we have to target one apple at a time. Then we use a closed loop system which includes sensor and other and my work thing, which is a vision based system, to accurately and precisely navigate to that point. So that's the system diagram. This weird thing is kind of like the manipulator. We will see that in the pictures that how it looks like. But essentially this gray thing is like a retractable pneumatic fabric based extending arm which have 4 degrees of freedom. It has one camera at here and another camera at the hand where an end effector needs to be attached. The system control diagram at high level, it consists of these particular factors. I am using encoder. I'm not just neglecting that, but I'm just complementing it with my vision system to improve the accuracy. So that's kind of like a physical system. We can come up if someone has questions regarding that. So the decision module that consists of like the vision module, which consists of 2 cameras in my case. Then there's an actuation module which involves getting the feedback from the vision system and having the transfer function associated to control the overall manipulator. And then there's a part. So this is not chronological, these are just the elements. So, and the other thing is like distance estimation and detection, which is an AI based part of my project. So that's the experimental setup. This arm which you see, it's like a balloon thing. It's made up of nylon based carbon fiber infused nylon based fabric, which is very lightweight and have really high susceptibility for perforation. Yeah, there's a thing where you mount the local camera and then there's the global camera. So that's the physical setup. When it comes to like the vision and detection part, I'm using YOLO. I mean, I don't have to reinvent the wheel to make up another new model. Just use whatever is available. And it is primarily to detect apples in the various lighting conditions which one may face in orchards. So these are like the multiple lighting conditions, weather and time of day on which the model was tested. So that was like the vision part. Okay, so I have 5 approaches actually which are iteratively done in order to prove my hypothesis that vision-based manipulation for soft robotic arm is really a good option. So first thing, the first approach, it involves no feedback, neither encoders, nothing. You have a mathematical model of the robot and you just send the control command and send it. The other one involves closed loop control, which includes feedback from encoders, the traditional disk encoders. The third one involves a global camera which is doing visual servoing